before we get to our first talk, there is a standard set of marketing slides we received from RISC-V International to give at the start of each of these meetups, but I don't actually have an up-to-date copy of them, and I can't help feeling that most people who are here understand that RISC-V is an open instruction set architecture specification, originally coming out of the University of Berkeley, and the work particularly led by Krista Osonovich and Dave Patterson. So it has become very widely popular around the world, and I know we have people attending here who are very significant players in the RISC-V world, as well as a number of people here who are here to learn more. That's the whole point of the meetup. I'm not going to say any more. If you genuinely wish to know more, we have Q&A at the end, so please feel free to ask any questions, and there is a multitude of material from RISC-V International available online. So that's this is a meetup. People were putting their hands up, asking questions in general. If we were in person, please do the same. You should be able to raise your hand. My colleague Sarah Cook will be keeping an eye for people raising a hand and making sure that the speakers can see that, and we will just take questions as they go through. Okay, so I'd like to hand over to Isaac, Ren, and Ethan, who are going to give our first talk today about their work trying to create the world's smallest RISC-V AI processor. I'm not sure which one of you is going to lead, but over to you.
Yeah, do you want us to turn our cameras on for this?
Yeah, please do. When you're speaking, please turn your camera on. I'm going to turn mine off because I'm going to stop speaking.
Right, and then I have to figure out how to share screen on Zoom.
There's a should be a share screen button.
Ah, yes.
Okay,
it's disabled, apparently. The host
Sarah,
disabled.
okay, let me just enable it for you. Oh no, these have been locked by the admin. Is BCS London still online? No, they've gone away. Okay, Sarah, are you able to enable that?
No, unfortunately, only the account holder can. Can the speakers please either email their presentation to Jeremy or myself, and we will have to screen share for you.
Okay, we'll try to do that very quickly.
Who are you sending it to, Isaac? To me?
I'll send it to you, yeah.
Yeah.
Right.
What technology have you used for your slides?
PowerPoint.
Right, okay. I will see if I can get that to open.
I can save it as PDF if you want.
Yeah, that's probably
Maybe.
safer, given that the ability of LibreOffice to mangle PowerPoint and vice versa is legendary.
Okay. Right, the attachments. Right, you should have received an email.
Okay, while I am just getting that up on the screen, perhaps you'd like to introduce your team.
Okay, yeah. So I'm Isaac. I'm a fourth-year computer scientist at the University of Southampton, and I'm joined by Ethan Lim. Do you want to introduce yourself?
Yeah, I'm a fourth year in electrical engineering from Southampton.
And also Ren Chen.
I'm also the engineering in Southampton.
Okay. We also did this project with 2 other members of our group, Daniel Zelinka and Amdadullah MD, but they couldn't be here tonight. So yeah, I'll while we're waiting for the slides, I'll briefly overview the. Oh, there it is. Okay. Right. So
just say next slide and I'll move it forward for you.
yeah. Okay. So we're going to talk about what we did for our 4th year group project, which the title that we were originally given was creating the world's smallest AI processor, and it's somewhat developed since then. So if we move on to the next slide. Yeah. Oh, sorry. Yeah. There's a structure of the talk. I'll begin with an overview of our project, and then I'll cover our motivations, a couple of related projects that we looked into, and then I'll hand over to Ren to talk about the design of our vector accelerator that we made, and then Ethan will talk about our benchmark software and results, and then at the end, I'll talk about some issues we encountered along the way, because Jeremy, this was done in partnership with Embecosm, so Jeremy has been helping us along the way, and he mentioned that no one seems to talk about when things go wrong, so we thought we'd add a little section at the end about it. Next slide, please. So yeah, in a nutshell, our project was developing a vector accelerator for the RISC-V serve core to improve performance in typical embedded machine learning workloads, such as neural network inference. So I'll assume, since this is a RISC-V conference, we all know what RISC-V is, and Jeremy just explained it minutes ago. But a vector accelerator is an extension module for a processor which adds support for vector instructions, meaning instructions that can perform an operation on multiple data values at the same time. So Serve is an award-winning processor developed by a very smart chap called Skålof Kindgren. It uses a bit serial design, which means that instructions are executed 1 bit at a time. For example, an addition operation would take 32 cycles to execute, since it's a 32-bit architecture. So like the least significant bit of each value would be added, and then a carry bit, and then it would continue using the same hardware for each, which significantly reduces the logical size of the processor. And as such, Serve is supposedly the world's smallest RISC-V processor. Neural network inference is the operation of using a trained neural network to infer a result. For example, the likelihood of a given image containing a person or something. Next slide, please, Jeremy. So some brief motivations of why this might be interesting to people is, what's the motivation behind doing this, is that smaller machine learning hardware, like a minimal serve core, could be synthesized on very minimal hardware. So that it's easier to embed smaller things into other products. So for example, we found an article at some point about hearing aids being limited because you can't fit good machine learning hardware into them without being obtrusive. So that's a potential use case for smaller, capable machine learning hardware. Also, if it's cheaper, then it's more accessible, so more people can get into hobbyist embedded machine learning challenges and things. Also, smaller microprocessors tend to use less power overall. And as a far-fetched idea, a smaller processor is more scalable into a parallel network, so it opens up opportunities like massively parallel neural networks more easily. Next slide, please. So yeah, there's a couple of projects that are relevant. Firstly, in 2020, another 4th year project from the University of Southampton carried out a similar project where they developed a vector accelerator for an open hardware group processor, the CV32E40P. So they achieved a 7 times performance increase in a machine learning benchmark using their vector accelerator. So a lot of this project was similar to their work, but for a different architecture. So it was very relevant to us. And also the serve has been extended previously with support for the multiplication or the integer multiplication and division extension as part of the Google Summer of Code 2021, which is a good reference for us for extending it with. vector instructions. Next slide, please.
Yeah,
So, yeah.
and thank you, Isaac. There are about three opcodes and 16 instructions in the vector extension, and we have tried to support like 8 of them, and they are the unit strikes and strike and index for both load and store for vectors. And we have also got 3 instruction for vector of arithmetic, and also 1 for the parameters configuration instructions. And they're all listed on the left of the slides, and at the right of the slide is a very overview of the design diagram of our vector accelerator. And yeah, and what happens is that when a server has low instructions and one is belong to a vector instruction, it will pass the execution to the accelerator, and then therefore the accelerator will just start, it will be just being kicked off and then start its execution. And also based on which type of the instruction it is, like it will do either the memory accessing or calculating 2 of the vector register that it has been stored already in the accelerator. And next slide, please. Yeah, and then there are several, like how many of them? Yeah, there are 12 arithmetic instruction is being supported, and just by selecting the correct bit field, like just by feeding the correct bits in the bit field font 6, and yeah, like about the addition, subtraction, and also the saturation, addition and subtraction is like will also work in our vector processor. And next slide, please. Yeah, like yeah, for adopting our vector processor, we have to modify the original serve, which is the processor we are building on, and also the memory file. And one of the issues we have faced is that it's quite difficult to modify the serve, like the code module correctly, is because the serve is highly optimized. Therefore, there are always some like most of the operations, they are only evaluating like 1 or 2 bits of instruction. Therefore, once we have introduced our new opcodes, although it's like 7 bits for each opcodes, but it might accidentally have make the serve just went into the unexpected behavior. So which has bring some issue, like when we were in the debugging for like when we bring both of our vector processor and the modified version of serve together. And also the serve will execute in 2-stage, like it calls itself as a 2-stage mode when when execute with any external units. Therefore, there will be about 64 clock cycles, like as a not as a penalty, but as a trade-off, like to get use of any external units. And our accelerator is regarded as an external unit for serve. So we might so we also have to use that 2-stage mode. But the serve itself is as Isaac has said, that it will execute most of the instruction under the 32 cycles with 1 instruction. So therefore, we are using 2 of them is not a really big penalty, or or it's a very cheap trade-off for that. And next slide, please. And it will be the benchmark result and will be talked about by our teammate Ethan. Next slide, please.
Hello, I'm Ethan. I'm here to talk about benchmark software. So, using our VPU, we implemented 4 operations: the vector add, ReLU 6, and matrix add. So to benchmark these 4 operations, we created a simple software. It measured the amount of clock cycles to perform each of them with and without the VPU. we tested each operation with different element length, different number of elements. So 48, 16, 32, 64. And we tested with and without the VPU in order to measure how much of a performance piece the VPU would give us. Next slide, please. So these are the results from the benchmark. As you can see, the VPU greatly enhances the performance of the operations. In next slide. Next slide, please. Thank you. All four benefit from the vector operations. Next slide, please. And these are the values if any of you are interested. For the vector, for with the VPU and without. Next slide, please. And now Isaac's going to come back to talk about what went wrong with our project.
Yep, thank you.
Next slide.
Next slide. So originally, this project ran from October until last week, although we had a report to write for the university. So of course, that was, towards the end of the project, we could do less practical work. So originally back in October, we set out with a lot of goals that we wanted to do. It was like, oh, we'll implement all of the instructions that were proposed by the AVA group I mentioned previously as like a minimal AI focused subset of the vector extension. We thought, oh, we can modify the tool chain to support this subset of instructions. And then once we're done, we'll optimize our accelerator for logical size, measure its performance using a standard benchmark instead of our custom benchmark software, which was adapted also from the AVA group, I should add. They had a test bench they used, which we adapted for it. And we thought we'd synthesize our accelerator on an FPGA, so it's a more feasible, like usable result, actually running it on hardware. However, if we move on to the next slide, we'll see that in reality, all we managed was to implement a minimal set of instructions that we needed to demonstrate the viability of our VPU for vector like acceleration of machine learning, or not even specifically machine learning, but of our benchmark program. We had no time for the toolchain work. We didn't manage to optimize our accelerator for logical size. And yeah, our benchmark wasn't standard, as I mentioned. We failed to bring up a standard benchmark. We actually wasted a lot of time on that and had to abandon it in the start of December or the end of November. And we were unable to synthesize our acceleration on FPGA. So I'd like to mention that, like, a key issue that we've noticed upon reflecting on this project, like why were we unable to meet a lot of these goals, is that we didn't do much initial research when setting out, or we did some obviously, but I think it would have been more beneficial for us to in-depth plan our entire, what each step would be for these targets, whereas we just sort of skimmed over what would be required implementation wise, which has led to us doing working inefficiently, or sometimes doing work in the wrong direction. So which slowed us down drastically. So I think this project should be a big recommendation for why you should spend time planning your project and before you start and before you agree to deliver something to a customer like Jeremy. So yeah, well, we if we move on to the next slide, you can see, yeah, and in summary, we developed a vector accelerator for the serve, which does successfully improve performance. And we did it because of the reasons mentioned previously, where smaller AI capable hardware is useful. There's use cases for it. And yeah, also I'd like to finish by saying all our work will be open source after our university deadlines and things have passed for reasons like limitation wise we have there. And if that's, I think that's everything. So if there's any questions about our talk, we'd like to answer them.
So I open up to the floor for discussion of this, and I think it's a very candid talk. At these talks, often everything is presented as though it all worked perfectly. Now, I was the industrial supervisor for this project, and I think would it be fair to say that one of the things you guys have learned from it is project management requires a certain amount of ruthless decision taking early on?
Yes, I think I mentioned originally we intended to use the TensorFlow Lite micro library and adapt that to use our vector instructions, so we could use a standard benchmark. It's like the TinyML-Perf benchmark suite. However, we got to the end of November and we had no like tangible progress for that, so we had to abandon it, and we should have abandoned it sooner, because that also caused delays with people not being available to work on other things. So I think it's important to make decisions as a project manager. You can't just put them off.
Okay. Any questions from the floor? Please join in if you wish. One thing I'm curious about is you presumably have an idea, even if you didn't actually get it working on FPGA, about how big your coprocessor is, and in particular how big it is compared to Serve, because Serve is tiny. I think the record is you can put 10,000 of them on a big FPGA. So how big was your vector processor by comparison?
Quite large.
Yeah,
Go for it, Ren.
Sorry, like we didn't really compare like what are the two sides, but like based on like, because we are using like our vector length is about 256 bits for each vector register, and then like for the vector extension, like they are asking for 32 of them. So yeah, compare with like only looking at the register file, like the coprocessor is already relatively big, like compared with a single Serve core. And also I've used a massive like lots of like multiplexer for feeding like each element of the such a wide like a vector register. So I assume like you will have at least like one or twice big, like a bigger than original Serve, I assume.
Probably a lot more. And also we had to modify the original Serve, so that gets a size increase as well.
Yeah.
So yeah, because the plan for the project was to start by developing a basic working accelerator and then optimize it for size, but we never had the chance to optimize it for size. So.
And am I correct that unlike Serve, your Serve is bit serial, so it does one bit at a time?
Mm-hmm.
But am I correct that you are actually doing the whole vector at a time? So you're more like a conventional vector unit. You weren't trying to do a bit serial vector processor.
Yeah. I think that's correct.
Yeah.
Okay. And okay, so
a question in the chat.
Oh, a question in the chat. Yes. Oh, yes. That's the other place you can ask questions, in the chat.
We've not personally thought about much of this because it was part of a Unity project. So, but I'm not incredibly familiar with PyTorch, but that might be an interesting.
Hey guys, pretty nice work. So it's TinyGrad is like 1,000 lines of Python code, like the neural network layer, and then you can basically add your accelerator. It has like MLOps and low-level operations, and basically you have to implement the low-level operations. There are like 16 of them or so, and yeah, I think it's much easier to add your accelerator to TinyGrad than say TensorFlow or PyTorch, because in those libraries there are more operations.
Okay, yeah, that might have potentially been a better approach, but yeah, as I said, we didn't do sufficient research before beginning, so yeah, that might be an interesting project actually.
So Ahmed, is PyTorch software or hardware?
Well, PyTorch, I guess, kind of both. Like, you have the software layer, like the high level, the neural network layer, and then basically through kind of lowering, as you write accelerators for PyTorch, you get closer to hardware, but it's still software basically, but it goes from the top down to the low level operations.
Yeah. So you could look at, for example, when you know what the low level operations is, implementing them on your processor.
I'm sorry, I didn't get that.
So what you could do with PyTorch is, once it's gone down all its layers and you've got to the low level operations, you could look at implementing those low level operations,
yeah, exactly,
rather than the vector ones chosen here. Certainly an interesting approach, and that might be something worth proposing, either as a Google Summer of Code project through the Free and Open Source Silicon Foundation, which is where we've done some of this work in the past, or reaching out to Southampton University if you're willing to supervise it as an undergraduate project. As a master, if they're masters, it's a 4-year degree, so it's the MSc project. So yeah, it's an interesting idea. We started. This is now the 3rd year I think this project, a variant of this project, has run, and the choice of using the vector instructions was sort of, well, let's take something that's there and then take a subset. But PyTorch might give you a suggestion for a better set of operations.
Yeah. I think it is worth pointing out as well that the project is only, it's meant to be about 12 weeks of practical work, so it's not a huge time frame to do like the whole software to hardware workflow.
So
We have another question.
Go ahead.
Yeah, how did you come up with what instruction to implement first? Oh, well, like us, because I've designed most of the hardware, so I should be able to answer that. And what I was planning is that, just look at the specification, and then I just choose the unit drive for in loads and store, which you have which will enable the very basic minimum fetching element into our coprocessor. And also I've just built a very tiny a 32-bit ALU. So and then which is can't remember exactly which one instruction instruction was it, but those 3 instruction was the initial instruction I've chosen, just for making sure that the coprocessor can work with these. And then we have extended into strides and index in low-end store, and also we have extend our ALU to support different operations.
So yeah, in summary, we had to implement a minimum of loading the vectors and storing the vectors back into the memory file. So those had to be the first instructions, otherwise we couldn't do anything observable. And once we had that, there's also a configuration instruction for determining what size vectors you have. And then also we had to have some sort of functional operation. So we opted for add because it was, I think you hardware people thought it was one of the simpler ones, and also it was used in the vector assembly functions that we were adapting from the AVA group's work.
Yeah, it is.
So, and there was no other dependencies in that function, so it was a isolated thing that we could implement and test.
I think if we go back a year or two and look at what the AVA and GSOC people have done in the past, the approach taken there was to look at, they did have TinyML perf working because it was a different processor. And they looked at what were the low-level functions that they would want to implement. And it was done by hand-coded assembler for the low-level set of low-level functions, and what was the minimum set of vector instructions that would make a useful difference if you were hand coding these low-level kernels. And that then came to the same thing: is you need to be able to load a vector, you need to be able to store a vector, and you need to be able to do a small number of arithmetic operations on a vector. And I think AVA came up with a total of 8 instructions, which is about the same as you've got here. So that was the approach. And the original approach didn't know if it was the right answer. It was really trying to ask the question, is this a sensible thing to do? And the same as the guys reported in the past, they've got a 7-fold speed up. So that was where the historic set. And then then this year's team picked up that work and looked at what was feasible to do with serve, which is a very different sort of process.
And also, yeah, our minimum speed up was 60% in the most machine learning relevant operation, which was the matrix addition. And that scaled upwards with the length of the vectors. So it is probably viable if we could optimize for size and maintain some of that acceleration.
It's a good question, and it is an open question as to if you want to go down the principle of what is a small number of instructions to add to RISC-V for AI inference, and this is narrowly AI inference, it's not for AI training. What were the set of instructions you should have? How big should the vectors be to give you a useful trade-off? And those are sort of open questions, and all the previous materials on GitHub under the AVA organization, this will appear. The university doesn't allow you to publish until your exams have been marked. Marked, or is it submitted? So I think they probably can open source in a week or so. And then after that, yeah, we welcome others who want to go on, and we do try and carry these on through Google Summer of Code. So it's not meant to be exclusive at all. So yeah, yes, if Martin, if you or your colleagues would like to have a go at you know, suggesting how this could move forward, it'd be very welcome. Right, are there any more questions? Any more comments? This is not just questions, it's comments, suggestions. We've had a couple of good ones today. Okay, so thank you very much. So, oh yeah,
that was me posting the open source link. Yeah, you've posted where your work will be. So thank you very much. Well done with your project, and in a week's time you will have your final presentation, and then your free team. Yes. Okay, right. Okay, thank you guys. So our second talk is a tutorial on how to add built-ins to the RISC-V GCC compiler. It is GCC specific, this one. In the future, we'll look at how we can do the same sort of talk for LLVM. So I will set this up as a slideshow and share it. Yeah. So hopefully that's good and visible. So I'd say this should have been given by Nandini Jamnadas, who's part of the Embocosm team. Nandini is the head of the GCC project for the Open Hardware Group. For those of you who don't know the Open Hardware Group, it's one of a number of industrial consortia developing commercially robust and open source RISC-V processors. There's the CHIPS Alliance, largely based in California. There's the Open Hardware Group, based in, well, headquartered in Canada with members around the world. There's the Low Risk team in Cambridge, and there are academic institutions that act as consortiums. So there's ETH Zurich and the University of Bologna with the PULP initiative. So within the Open Hardware Group, we have a software task group, and within the software task group, Nandini leads the project to bring up the GCC toolchain. And
I say she was due to give this talk, but I've offered to give it on her behalf. So any mistakes are very definitely mine, not Nandy's. So first of all, please interrupt if you have any questions through the way. This is a tutorial. So what is a built-in? A built-in is very much a GCC term. Other compilers sometimes refer to these as intrinsic functions. Confusingly, GCC also has intrinsic functions, and they're not the same as built-ins. Okay. From a user perspective, it looks like a regular C function, except it probably begins with __ built-in. Okay, but it's not written in C or assembler or anything and linked in. It's intrinsic to the compiler. It's built into the compiler and implemented directly within the compiler. And it comprises patterns to be matched in the machine description. And both GCC and LLVM are pattern matching compilers. They look for patterns in the code that's being generated and use it to create new code. Okay. And the most common use of built-ins is to access machine functionality that isn't readily accessible through high-level programming languages. So you may have, for example, instructions to control caches and so forth. And the compiler will never, is very unlikely to generate those instructions automatically. You want to wait to tell the compiler to generate them. Now, for RISC-V, it presents an excellent opportunity to expose ISA extension functionalities. So let's see how you add a built-in function. And I'll give a bit of context before we get into the nuts and bolts of how you do this. Okay. So here's an example of a built-in. Okay. Now, one thing about built-ins is you don't need the headers. They're built into the compiler, so you don't need math.h. Okay. So here is a simple function foo that actually computes the square root of 4 and assigns it to a float variable called float using the built-in version of the float square root function. Okay. Now, it looks just like a function. It will compute the value 2.0, and if I were to return it as a result, I could print it out. Okay, and it's a standard built-in function for GCC. It's not a real function though. It doesn't have an entry or an exit in the same way that a real function does, and you can only call it as a function. You can't take the address of it and pass around a pointer to this function. Okay, so it is a construct within the language. It's not a true function. Okay, and why would you do this? Okay, because actually, if you try using this on x86 or for that matter RISC-V, you'll see it just generates a call to the library function square root f. Okay, but one of the reasons you have this is that if you have an architecture that perhaps has a square root instruction, and that may seem strange these days, but in the past, architectures like the VAX had instructions that would do this, then this would give you a mechanism for automatically generating the instruction. Okay, so as I say, it's so that's why you have them. Square root perhaps is a little unusual. In other cases, there is more opportunity to access the real hardware. And there are loads of standard built-ins. Okay, so if you go to the GCC source tree and look in the file gcc builtins.def, which looks a bit C-like, but it's a definition file, so it's not true C. Okay, and you will see a whole load of macro calls to define various built-in functions. Okay, so you can see in the middle there, def 99 to 90 res _ built-in. So this is specifically the macro for generating built-ins specified by the C90 and C99 standards. And you'll see built-in squirtf. The name is squirtf, but it will be preceded by _ built-in _. And it tells you what the type is, and it takes a float and returns a float. So it's a function float, and it's got some attributes, and it's got attributes associated with floating point error handling. And one thing about the built-ins is they are guaranteed to do IEEE error handling. Okay, so that's where standard built-ins are found. Custom built-ins are typically found within the GCC config for the particular architecture. So each architecture has its own config directory. So in this case, in the case of RISC-V, gcc/config/RISC-V, and then the definitions are in, you can find, you look in RISC-V-builtins.cc, and that is a C++ file. Okay. So the obvious thing is, why not just use inline assembler? Okay. GCC, and for that matter, LLVM, allows assembly code to be specified in line, __, __, open brackets, and then a template for the instruction where we substitute the arguments, %, 0%, 1, then a colon, then the output, any output operands. In this case, we've got one, which is a variable called res, and it's of type =R. In other words, it's got to go into it's going to go into a register, and it's going to write a result into that register. That's what the equals means. And then a colon, then any input arguments. In this case, we've got one input argument. It's a type M, which means it's a location in memory. And that location in memory will be some sort of variable. In this case, we've got sema. And the GNU compiler will carefully make sure that the value of the variable res is being held in a register that can be substituted in there, and it will substitute the correct instruction. And you can compile and assemble that, and it will generate the instruction. There's a number of reasons why inline assembler is not very nice. It's a black box, and it has very limited data flow information to tell you how data flows through that instruction. And modern optimizing compilers are crucially dependent on data flow analysis throughout the program. And that allows them to do optimizations that allow code to be hoisted out of one function and put in another, for constants to be folded, for common sub-expressions to be simplified, and so forth. Okay. The optimization with ASM is more or less limited to selection of how you get values into the arguments. So how do you get res into a register? How do you make sure that you've got access to sema in memory? Okay. But you can use them without any more effort. So very easy to use inline assembler. Okay. But you can cripple performance if you're careless in your use of inline assembler. Built-in functions offer some advantages. They have the full data flow information. They're within the compiler. They have all the data flow information. So they can be fully optimized. Okay. They are based on pattern recognition. And if that pattern occurs elsewhere, it can also be used by GCC. So not just when you call _builtin, but if for some reason that pattern appeared in the internal representation in the compiler, it could also use that instruction. So potentially you're getting a bit of a pattern matching optimization for free. And being within the general pattern framework, they're generally available to be optimized. And we'll have a look at that a bit later on. Okay. So CV32E40, I've typed that, I should say CV32E40P, not 4E, okay, ISA extension. Now that's one of the open hardware group's Core 5 specific cores. So Core 5 is the brand name for cores developed by the open hardware group. CV32E40P is a particular one, okay? And it's a standard RV32 IMAFC core with 8 ISA extensions. Okay, these actually come out, the whole stuff comes originally out of the PULP project at ETH Zurich at the University of Bologna. So the 8 groups are, they've got post-incrementing load and store instructions. Okay, they've got hardware loops, nested hardware loops even. They've got some direct branching, immediate branching operations. They've got a number of general ALU operations to extend the ALU operations of RISC-V. They've got a set of multiply accumulate instructions. Okay. They've got event load, and we'll look at event load later, which is about control of multi-core systems. They have got a set of SIMD instructions. That's a bit like the standard P extension, but it's defined by ETH Zurich. It's not the standard one. And they've got their own bit manipulation, again, coming out of ETH Zurich. Okay. This is now on its second version of Silicon. Those last 3 are only in the second version of Silicon. Okay. So it's a big thing, and those are big. There's something like 220 instructions in those extensions. Okay, and many of them are not going to be generated directly by the compiler. Okay, so we're going to add some built-ins. We ought to think about how you name your built-ins. Okay, general convention in GCC and LLVM is that the convention they're called __ built-in _ and then the name of the built-in. So RISC-V standard built-ins have the name _ built-in _ RISC-V, and that's a general convention. If you're target specific, put the name of the target in the built-in name. Okay. RISC-V has the concept that not everything's done by RISC-V International. Vendors can add their own extensions. So you have a convention for vendor-specific RISC-V naming. So, and that's already, we don't have that yet in GCC, but in LLVM, you'll see a number of instructions that are _ built-in RISC-V _th. And those are a number of built-ins defined and contributed by Alibaba's T-head processor division. Okay, so you have a vendor and then a name. Now, Core 5 has so many built-ins, we were a bit concerned that just having them all in one bunch might be confusing. So we've gone one further and we said ours is going to be called _ built-in because they're built-ins, RISC-V because they're RISC-V, CV for Core 5 because they're part of the Core 5 architecture. And then we're going to subdivide them. We're going to put the name of the ISA extension. So they'll come in 8 groups for our architecture. And then at the end will be a name. Okay. So let's move on from there. Okay. And we're going to look particularly in this example at the event load word instruction. So this is, excuse me a moment. Apologies for that. I have a set of headphones that in the absence of anyone talking will switch themselves off after 10 minutes. Okay, so let's look at event load word. This is for clusters of cores. So it's only supported in multi-core systems. And it performs a load word, but it can put the processor into a sleep state, and that's documented in how the cluster extension works. Okay, so it's a very straightforward instruction. It looks like a load instruction, but it has some side effects. Okay, now you can't generate this from C. There isn't yet any magic attribute you can give to C to cause it to generate an event load word. So it's an obvious candidate for a built-in instruction to allow you to generate that. Okay. And what we've got here is the page from the CD32E40P version 2 manual, and it tells you what the operation is. It's event load. It tells you what it does and what its assembler mnemonic is, and it tells you its encoding. Okay, so this is a standard RISC-V encoding. It's sitting in one of the custom opcode slots, so it's not trampling on any existing opcodes, and it uses the func3 field to distinguish the fact that this is ELW. Okay, and it has a 12-bit offset, just like any other load. So that's the instruction. Let's move on. All right. Yeah. So let's look at the built-in. So we're going to define a built-in. Okay. So this is something that loads from an address in memory. Well, an address in memory, and apologies, that should be 32T, not 32. I've mistyped the slides. Okay, so it's a 32-bit pointer, and that will generate an event load word, which puts something in RD. Well, we may as well pick up RD, so the function can return the result of what's in RD. Okay, so UN32T. Okay. And here's an example of it in yours. We'll have a global variable SEMA, which is an address in memory. Okay. And we'll define a little function called foo. Doesn't have any arguments because its job is to call the built-in using the address of the variable SEMA, the global variable SEMA. Okay. And we'll return whatever the ELW gave as the result. So let's look at how we're going to implement that. Okay, are there any questions at this point? Okay, so let's look then. So let's look at what happens with the event load built-in. that example, if we generate with no optimization, we can see how the compiler loads the word load upper immediate with put the high bits in. This is how you put a high into a register, you address into a register. You have to do it in 2 instructions. First instruction puts the top 20 bits into A5, and then we add to A5 the low 12 bits. And so now A5 holds the address of SEMA. Okay. We notice, so then we can call cv.elw with an offset 0 on that address and loading into A5, and then because the results of functions going to A0, we're going to have to move the result into A0. But that's the simple and basic pattern, but this has got all the power of the standard RISC-V optimization to GCC. So if we turn on a bit of optimization, we can observe that we only need to worry about loading the upper 20 bits. And load upper immediate sets the bottom 12 bits to 0. Okay, so we've got the bottom up there, but we don't need to create the full address because we can have a 12-bit offset in ELW. So we can use the low 12 bits as the index onto that A5 we just loaded. And then, of course, why are we putting the result in A5? Let's put it in A0 so it goes straight into the result. So we can see we've generated an ELW for that address in memory in a minimal set of instructions. So before we add the extension, we need to think about, before we add the built-in, we need to make sure that GCC understands the extension. Okay, so if you look inside RISC-V common.cc, there is a struct which is a list of the extensions and their versions. Okay, and these are all version 1.0, so that's easy. So we've got 3 extensions here. We use XCORE-V as a generic extension in naming, so you can say RV32 in the architecture. You say RV32 IMIC underscore XCORE-V to mean all the ISA extensions. Okay, that's a shorthand that will probably go in the final version. Each of our extensions has a name that is XCORE-V and then something describing the extension. So, for example, we have XCORE-V ELW, which you can add to your architecture string to get the event load word extension. And we've got XCORE-V SIMD, which you can add to your instruction to get the CORE-V SIMD extension. ELW is an ISA extension with 1 instruction. CORE-V SIMD has the best part of 200 in it. Okay. So first of all, we have to add to that table, give it the textual name of the extension. Okay. And these can all go in ISA spec class none. That's fine for these general things. Okay, so we don't have to do anything funny with the ISA spec. Okay, now this is a grouping together. Okay, so this is allowing you to tell things are implied. So I've told you that XCORE-V was being used as a general catch-all. So this is saying that each of these here, and I've got another 6 to add. I've just shown you 2 of them, ELW and SIMD. These are implied by XCORE-V. So we need to say, if we've got a generic thing, we're going to have to imply it by XCORE-V. If we get rid of XCORE-V, we won't need this. Okay. Now, okay, so we better have a set of bits to tell us which of these extensions are enabled. Okay, so for each of our extensions, we'll create a mask to tell us which extensions have been specified in the architecture string. And so the generic XCORE-V is just 1. Mask XCORE-V, we shift it 1 bit up. SIMD, we shift it 2 up. Okay, and then we have a number of Boolean things to say, okay, I've got my RISC-V flags and I masked them with these masks. Was that flag one of the ones that was set? So I'm going to define myself a set of macros to tell me if this particular flag was set. Okay, and that thing RISC-V XCORE-V flags is a global variable that's going to carry the flags around, and you have to define those in RISC-V.op. That's where you define all your target specific variables. And so it's not a C file. It looks a bit C-like, but we're going to define an integer variable to hold the list of all the flags. Maybe that should have been unsigned in because they're flags. Okay. Now, what we're going to do now is going to try and map the names. Okay, so this table here, which is also in RISC-V common.cc, is say if you see X core V, then take that variable X RISC-V X core V flags, that variable to define, which is part of the GCC options class, and set the mask X core V bit, so set 1. If you see ELW, set the mask X core V ELW, so set 2. You see X core V SIMD, set the mask SIMD, which is 4. Okay, so that's how the bit flags get set in. And this table will be used by the architecture parsing in the command line to work out which options you specified. Okay. Now, here's the big one. Inside the RISC-V builtin.cc, the RISC-V target things, is a macro. Okay, and it's called RISC-V builtin. Okay, and what it does is it creates a call to a constructed function, which is where the compiler will start hooking in. Okay, and so we're going to have to use this function for ELW, and it's got a number of fields. Okay, it's got, the first one is instn, and we'll come to instns in a minute, and that is the critical one because that's the pointer to that's the name of the instruction pattern in the machine description file, and that is the thing that will make the compiler generate the code that we want. Okay, name is the name of the built-in function itself, so we've said what that is. The built-in type. Okay, so there's a number of RISC-V built-in types. There will probably be more in due course. There aren't actually in the official GCC for RISC-V very many built-in functions at all. The function type itself, okay, the function type itself, which will give both the return type and the argument types, okay, and then the availability predicate. And this is a predicate macro that's used to say, is this particular built-in available? Okay, because I'm only going to make the built-in to set event load word available if we've actually specified the event load word instruction set extension. There's no point otherwise. Okay, so, and there we are. Here's where we've called it. So that's the prototype. So the code that we're going to have we'll have a look at this in a moment. The machine description pattern is called CVELW_SI. The name of our built-in is going to be _built-in _RISC-V, and then _CV_ELW, the instruction set extension, and the name of the instruction ELW. They happen to be the same in this case. It's a direct built-in. We'll talk about those later. And its function type is it's passed in actually a void pointer. We don't actually say it's specifically a 32-bit pointer. It's a generic pointer it's passed in, and it returns a USI. That's an unsigned single word integer. Okay, that's the GCC nomenclature for the type. Okay, and the availability function is going to be called CVELW. Is the ELW extension enabled? Okay. Now, my apologies for the layout here. I was doing some layout tidying up, but I ran out of time. Okay, this is the most complicated part here, and I'm going to give you an overview of GCC instruction patterns, but this will only be an overview, and when I train students on this, we have several days looking at this. So this is not, I'm giving you a first look at something. If you look up define instn, you will get on Google, you will get the GCC internals manual, which will tell you a lot more. Okay, but this is how you define patterns in the machine description. Okay, so we said the instruction, if you look at the group, we said it was called CV_ELWSI. All of them, because this is a RISC-V function, are going to be preceded by RISC-V. So the name of this instance is RISC-V_ and then the name we gave. Okay, and the first thing we've got is a pattern that we're trying to match. Okay, so we know this is a load. Okay, we're going to set a value from somewhere in memory. So set is the general pattern for things where you're trying to set something to the value of something else. Okay. And the destination we're going to be, it's SI, it's a mode, what's called, we're matching an operand. We're looking for something that is SI. So it's a single word, it's an integer. We don't at this stage, we're just looking for the size. We're not worried about whether it's unsigned or signed. Okay. And this is argument 0 in the pattern. Okay. So this is because in RISC-V destination confinement. So it's argument 0. So we're looking for the very first thing we're doing. We're trying to match something that's a single word integer, and it's a register operand. It's got to be something in a register. And at the end, we say we've got a bit of a constraint. Specifically, it's a register we're going to write. That's so equals are, the equals means writable. And you sort of saw that a bit in the inline assembler. It's exactly the same notation. Okay. So we're looking for the first operand being a register we can write. Okay. And then the second operand is specifically going to be volatile, because this is actually a volatile operation. Okay. So we don't want, so it must happen. It must happen once. Okay. And it's a memory. And we're looking for a 32-bit memory address for something that's a 32 value. And we're matching something that's a 32-bit address. It's the one, it's field 1, okay, as opposed to field 0. So the second, with the number counted from 0. Okay, it's an addressed operand, and and it's one we're going to read. And P just means any address of memory we can read. Okay, and lastly, we put an attribute with this pattern. It's unspec CV LD. I wouldn't worry too much about that. That's a bit of icing on the cake. I'm not going to go further than that. Okay, so that's the pattern we're looking for. We say if we can see this in the intermediate code of GCC, okay, that's what we're looking for going. Oops, sorry. Okay, now then we sorry, I'm not used to driving this particular. This is Google Sheets. Okay, so target. So we're looking for a number of things. Now these are those macros we described earlier. First of all, we've actually got to say we've specified X core v ELW as the architecture extension. Okay, and secondly, this is only for 32-bit architectures, so this is not a pattern you can use with 64-bit. So even if you specified the ELW instruction, if you've done it with an RV64, it's not going to work. Okay, so you've got that constraint there. Then you've got the actual pattern of what we're going to create. So if we can find that, what we're going to generate is we're going to generate cv.elw followed by a tab, then the first argument, which is %0, okay, and then the second argument, %1, but we're qualifying it, say specifically it's an address argument, okay, %0 will assume it's a register. Okay, so that's the pattern that what we want to generate, and there's more detail online exactly how to. And then lastly, the last bit of an instruction is optionally you can specify some attributes associated with this pattern. So we can say a couple of things is, first of all, it's a load, it's pattern for a load. Okay, it's a type of load, that's one class of instruction. Secondly, its attributes, its mode, GCC speak for a type. It's single word integer size. Okay, so the mode of what it generates is single word integer. Okay, and that's the pattern. And that is sufficient that if we say underscore built-in underscore ALW, it will generate the right patterns to get down there. Okay, now, so the built-in type, there's two there. There's built-in direct or built-in direct no target, and they really are specifying how a built-in function should be converted into RTL. RTL is the register transfer language, the internal representation inside GCC, the intermediate code, if you're familiar with compilers. Okay, and we've got two. One is the function corresponds directly to an MD pattern. Okay, and then the second one is it corresponds to an MD pattern, but with a return type void. Okay, so you don't need a result. Okay, of course we were RISC-V built-in direct because we do return a result. Okay, and the function type is the return type and argument types of the built-in. Okay, now you have to create these for yourself. So you create macros to define different function types. So we've got a function type for different function prototypes. Okay, and then you associate them with different address types. Okay, and one of the big things we had to do is RISC-V actually had very few of these originally, and we've had to create more because we've got a richer set of built-ins here. Okay. Sorry. Okay. Okay, let's try. Okay. So, yeah. Okay. So the last argument when we did this define, back at the time when we did that define of the built-in was the availability, and that's the name of the availability predicate. Okay. You define them with an availability with the avail macro. Okay. So what we've done here, you'll see we've added avail ELW. That's available if the target has specified X or the ELW and it's not 64-bit. Okay, and similarly we've done one for SIMD. Okay. So far so good, but it's important not just to write your built-in, but to test it. Okay, and there's two sorts of testing to do. One is to test that does the compiler work and generate the right stuff, compilation test, and the second thing is an execution test. Okay, I've generated this code. Does it do the right thing? Okay. Now at this stage we're only looking at compile tests, and that's because we'll be using a variolator model of the CV3340PV2, and that variolator model isn't quite available. We'll add execution tests when we've got them. Okay, so here we are. All we've got here is a function. We've said it's the things in curly brackets at the top are magic comments that guide the GCC test, Deja Vu test suite. Okay, so they begin with DG2. So this is a compile only test. Okay, and we specify the options when you do the compilation. You see we specify the arch is RV32I underscore XCore V ELW. In fact, we've explicitly specified its version 1.0, and we've specified it's the ILP32 ABI. Okay. So what we've done is we've created a global variable var. We're not actually going to use that. We've called a function int_foo which takes in a void address, okay, and it returns the result of calling ELW not with the address it was given, but actually with address 8 further up, okay. And how are we going to test if this is good? Well, for this stage, we're just going to scan the assembler, and we're specifically going to scan for cv.elw, was it generated? And because it's supposed to be volatile, was it generated only once? So that's the one there. So we're looking for just one cv.elw. Okay. And then we can run the test. And this is the log from here. And what you see with GCC, when you specify a test, it runs it with all sorts of different levels of optimization. And it tries using the LTO plugins and so forth. And it tries using fat LTO and so forth. It tries it with and without debug and so forth, and with compressed code. And what it's done is here, it says, first of all, for each of those, there's two passes. Okay, one is actually, did I compile successfully? And then the other is, actually the second one, and the first one is when I compiled, did I actually generate the right number of assembly instructions as scanned for? And this passes completely, and I think there's 9 different variants tried, each of which gives you 2 passes. So you get 18 passes. Okay. And that's all you need to do. Now, I have gone through this fairly quickly. So what I would say is it's to give you the pointers to allow you to get started. Okay. The way to look at this is all this code is in the Core 5 GCC, okay, and the corresponding assembler is in binutils GDB. So if you look in Core 5 GCC, you can find all these files and you can look at what's been implemented. and there's a bit more there. Okay, I've tried to keep it fairly short in a 45-minute talk. Okay, so that is the useful material for you to look at. If you want to get involved, we'd welcome you to get involved with the Open Hardware Group, and I know some of the attendees here are members of the Open Hardware Group. And if you really want to cut your teeth on this, there is a Open Hardware Group meetup every week at 9 o'clock in the morning UTC, 0900 UTC, okay, for half an hour, where the Open Hardware Group, Core V GCC group get together. Nandini chairs that meeting, and it is a purely technical meeting where we share experience, review code, and so forth. If you want to start doing this stuff, that's the meeting to join and ask when you get stuck, and people will help you. Okay, so I hope that's given you an initial view. I apologize that it's been me giving it. I'm not a GCC deep specialist. Nandini will be giving this talk again at FOSDEM, so you can hear the revised version by the author who really does know much more about this than me, who'll be able to tell you more of that. Okay, so thank you very much. I'm Jeremy Bennett and not Nandini Jamnadas. And are there any questions? Okay.
Just want to say thank you, Jeremy. It was very, very, very beneficial, very useful. I mean, it's always good to hear your insight, very well explained, and I appreciate being part of it.
Okay, glad you got something out of that. So any other questions? Anyone else? So I hope that was useful. I hope some of you might feel inspired to get involved. I hope it gives you some guidance on how to start adding built-ins. And as I say, I would encourage you to join in with the Open Hardware Group. We have mailing lists, we have meetings, we have a Mattermost discussion forum, and for the GCC, we have a weekly call. So, okay, thank you very much. That I will now stop sharing. That is the end of our scheduled meeting. Now, if this were an in-person meeting, this is where we would wander off to the globe for a pint of something suitably refreshing. Unfortunately, we can't do that now, but I will keep the channel open for a bit if anyone's got any questions, would like to discuss anything. And this is the whole of RISC-V. Okay, we've had 2 talks on specific subjects. Feel free to raise anything that you would like to discuss. And thank you to my fellow speakers, Isaac, Ren, and Ethan, for taking the time out from their studies to present their experience, and in particular having the candor to explain it didn't actually all go right and we had to change what we do. That's nice to see a talk like that.
Yeah.
There will be another RISC-V meetup, hopefully this time really in London, in 3 weeks' time. It's always on the 3rd Monday of the 1st, 4th, 7th, and 10th months. So the 3rd Monday in April will be the next London RISC-V meetup. If you have something you would like to talk about, bearing in mind that we try and focus on the open source aspects of RISC-V, then please reach out to me, and I will be happy to invite you to come and give a speak, come and give a talk. If you're in the UK, obviously we'd love to see you in person, but you can take remote talks for those who are not here, not in the UK. I guess one thing if anyone actually wants to suggest topics for the next meeting, I will try and find speakers who can speak to that topic. I think it's quite likely, given some suggestions I've had, that the next meeting we'll try and get some someone to talk about the RISC-V vector work, both from a hardware perspective and also from the challenges of getting RISC-V vector going on the software toolchain. Okay, I will leave the channel open for a few minutes, and then for anyone who wants to chat and talk to each other, and then I will close the channel. The recording will go up in a few days' time. So thank you all very much, yeah, enjoy our last few minutes chat, and then I'll shut the meeting down.